We're here to learn about redox. But first, we're going to learn how to cultivate balance. This is the part of chemistry that is very uniquely chemical. Chemistry. We're stepping into the realm of transformation. So we're going to learn this week how to write chemical reactions. And so first, we're going to learn to balance. The arrow separates the side. What we start with, the cause, is the reactants. And on this side, the effect are the products. Now, sometimes you have one, sometimes you have two, sometimes you have 3, 4, 5. But right now, that's it. The arrow separates them. So cause and effect, or reactants and products to a chemist. So you have to have the law of conservation of matter. You have to have the same number of each element on each side of the equation. There could be, I'm sure out there, somebody's probably come out with these steps. In my limited 25 years of experience, it's more practice. Like everything. If you just do the practice and go back and keep trying and keep the calm, keep cultivating the balance, the harmony in your life. I look at it as the big picture. Sure, there's one P on each side. Looks good. Chlorine. This is the lowest common number again. We have 2 and 3. So 6, we cannot change the subscripts. All we're going to do is fill in the blanks. And what we fill in these blanks are called coefficients. So we would need a 3 here and a 2 here. You can't break the compound apart. That's what it made. So you put a 2 in front and that doubles the whole thing, which means you now have 2 P's. So we put 2 there. So we have 2, 3, 2. That's the idea. Now, you're going to hear me keep calling them coefish, because one year as I was writing that word, a student who was hard of hearing said, Dr. Sherpa, what do the coefish have to do with anything? And it was again one of those times I looked at her and I'm thinking, where did I talk about fish? And it was just how I say it with the whatever kind of accent I have from wherever I'm from. Yeah. All right. So let's try next one. You should pause me actually right now and try all of these. Because if we were in class, I would pause and make you all for the next couple minutes try them. All right. So you have me back off pause. So you could start with the boron. I look again at the big picture and I see the 3 and the 2 for the oxygen. If you did start with the boron, then you would get to the oxygen, you'd see the problem. You have to get to 6 oxygens. You can't break the compound apart. We can only put numbers on the blank, which means, oh, that big eraser I keep telling you to buy, you're going to use it again. Or you can look at the big picture. So we have 4 borons, and 2 times 3 is 6. So 6 oxygens. Now, there's all these cool gimmicks again online where they'll show you make a list. And that's wonderful. We can do that. But what I found, people make the list, they end up getting so consumed by the list, they never get to the next step. This is just the first piece of it. So see if you can do it just from going back and forth. But if you have to resort to a list, go for it. All right, so I'm just going to start here with the carbon. I have 5 carbons, the subscript 5. So over here, I put a 5 in the front of the CO2. That gives me 5 carbons. We'll worry about the oxygens in a minute. Don't worry about them. Let's do the hydrogen. Just going left to right. I have 10 hydrogens there, so I need 5 H2Os. Because 5 times that 2, that's 10. So we're good for our carbons and our hydrogens. So let's do the oxygens. So sometimes that last one, put a little circle through there. So the trick Over here I have 2. Over here I have a lot more than 2. So I have 5 times 2, which is 10. And then I have 5 more. This 2 is just the hydrogens we double. But there's only 1 oxygen in every water, so it's 10 plus 5, which is 15. All right, so over here we have to get to 15. Now, there's 2 ways you can do this. So just hold your horses, I'll show you both, and you're going to pick the way that works for this beautiful brain of yours. You can do fractions, and then you have to make coefficients do need to be whole numbers most of the time. There are exceptions. Again, for those of you going to the 200 level, we will see exceptions to that rule. But in here right now, so 7.5 times 2 is 15. If you do that, then you have to go back to not lose that dreaded like half point. You'd have to double everything. So you get 2, 15, 10, and 10. And that makes them all whole. Or you can be like, oh, I didn't like that fraction. It brings back memories of fractions. And so you don't have to do fractions. You can look at this one and say, oh, it's going to be one of those where she did that fraction thing. And you just say to yourself, okay. Get out that handy dandy eraser you bought and you say, I'm going to start over with a 2. Keep it simple. That means I now have 10 carbons because this number doubles this whole compound. So I have 10 carbons. All right. I have 2 times 10. I have 20 hydrogens. So over here, 10 times 2 is 20. So we're back to the oxygens. So I have 20 plus 10. So this is 10. There's 2 oxygens in every CO2 and 10 more. So can I get to 30 by multiplying by 2? Sure can. I get 15 times 2 is 30 and we're good. We're golden. We're ready to move on. Or go back and do it again. So you just hit that back 30 seconds or whatever. All right, let's try next one. So again, you can go left to right, 1 magnesium, 1 iron, or you can look at the whole big picture and you can say, what I'm seeing is that bromine. I got that 3-2 thing going on again. So to get to 6 bromines, I need 2 here. Yes, a double soul compound. We'll come back to it. And a 3 here. That gives me 6 bromines. So 2 times 3, 3 times 2. So now I need 2 in front of my iron and 3 in front of my magnesium. So whatever you do, cultivate the balance in all your activities so that we can all experience greater energy and vitality. What an awesome word that is, vitality. Now, getting upset at your teacher? Not really cool. That's the wonderful part about this. I'm videotaping, so I don't know if you're upset at me. So if you're getting upset, pause. Go yell at the ocean or the clouds. Or go and say, what beautiful clouds those are. All the clouds I see keep looking like angels these days. We want to see. Or what we attract, perhaps. All right. So, aluminum. Sure, I got 1. So there is a trick on this last one. And that is, instead of seeing this as P and 4 oxygens, you can add your parentheses. So it's a PO4. So I have 1 aluminum on each side. I have 3 chlorines. So I need a 3 over here. Don't, just keep going. 3 sodiums, 3 sodiums, and a phosphate. And it works. All right, so we're ready to move on and see why I'm dressed like this. And so it is that we're going to do red ox. So here's a little red. And so these are my horns. Not other kind of horns. Even have my little tail. I was hoping for a yak's tail. They're pretty awesome. And so red ox stands for oxidation reduction. And the acronym we're going to do is LEOGR. Here's Leo. Leo's here to help us. This is your big day, Leo. We're going to turn this so we can see over here better. All right. So what LEOGR stands for, this is the best acronym anybody ever taught me. O stands for the word oxidized. GR stands for reduced. Those two words need to be part of your chemistry vocabulary. So remember we talked about polar, nonpolar, and I said these are some of the most important terms we're going to use in chemistry. You change them to hydrophilic and hydrophobic. These are the other two. In your teacher's humble opinion, so much is oxidation reduction. So what do they mean? Well, the term oxidized means it's where Leo comes in. If you lose electrons, you're oxidized. If you gain electrons, you're reduced. And they call it a redox. We always talk about it as oxidized reduced, and then when they combine it, they don't call it an ox-red, they call it a redox. So I'm going to go through this whole get up go. And I had a student, and I went through this for like a half hour, an hour, and we did it. And she was so sweet, and she said, this was like 15 years ago. Well, I get all this. I get this gaining and losing, and I can figure out the oxidation numbers and all that. But what's the redox have to do with anything? And I'm like, what is she talking about? And this before I used to dress up, this back in my younger days. I'm like, what redox? So I did what all good teachers should do, and all good students, you take a sip of water to like slow down, give yourself a chance to figure out. And I turned and looked at the board, trying to figure out when I mentioned of redox. And there it was, up there. It's actually all one word, but it's like that periodic table, which is per periodic acid, which I see per iodic acid. And so I started dressing up like a redox. Got these shirts made in Nepal. So they have usually say yak yak yeti. And I got the guy to make me a yak yak redox. And so there you go. All right. So let's go through the steps. Oxidation reduction happens all around you. So go do this now. Go try this demo. Go get an apple and take a bite out of it and then put it down. What's going to happen? Well, it's going to turn brown. The oxygen in the air is oxidizing it. It's stealing electrons. So it becomes oxidized because the apple is losing electrons to the oxygen in the air. That's why it's called oxidation. Cut a potato, and then you get distracted, you come back. The potato's raw, it starts oxidizing. Cut the avocado, what happens? It starts turning brown, right? The guacamole, but it even makes it to the next day. It usually starts turning brown. That is oxidation. And so we have antioxidants, which are doing reducing. And so the antioxidants like vitamin C, they fill in those missing electrons. And it's just loaded in all the fruits and vegetables out there. Why you should eat your fruits and vegetables. So we're going to do oxidation numbers. Then we're going to put it back with those equations we did at the beginning. And we're good to go. So we're going to walk through the steps for assigning oxidation numbers. And you already know these first two steps. Simple ions, those charges, I've been calling them charges. They're actually oxidation numbers. So if we have something like, let's say magnesium chloride. Magnesium we say is a +2, chloride's a -1. Well that, my dear students, that +2 and -1, you can see it good enough. Those are oxidation numbers. All right. An atom by itself, just hanging out. Like back there on the first page, the P or the Cl2, hanging out by itself, it gets a halo. Oh, it's 0. It's neutral. So it's 0. Oh, every time I put a halo, you get to sing like the angels. Leo loves doing that. That's his favorite part. All right. So we get to the part of the two nonmetals. So let's do an example. Let's say we have a compound. Well, we can do our PCl3 up there. So you have two nonmetals. The rule is, first, we're going to go through 3 steps. Step A is hydrogen will always take 1 for the team. Now remember, hydrogen's a nonmetal. So acids are 2 nonmetals, but the hydrogen's willing to take 1 for the team and says, I'll give up mine. I'll give up my electron to you. I'll take the +1. So when we ever see hydrogen in a compound, we're going to give it a +1. Happens in nature. By itself, it gets the halo. Ah! In a compound, it's a +1. Now, of course, there's an exception to that rule. And it's a man-made compound, and we're not going to run into those. You might in a higher level class if you want to, and that's awesome. All right. So step B, the electron greedy one. Do you remember the word for electron greed? The one that is more electronegative. Yeah, it wants to be greedy. It gets its common charge. Meaning like in step 1. So in these, who's the greediest of them all? It's like periodic table on the wall. Who's the greediest of them all? That would be fluorine, and then oxygen. Chlorine is closest to that corner, so chlorine gets a -1. Oh, but let's wait. It's not an ion. These are oxidation numbers. That's the big difference. Step C, this is, one of them has to take 1 for the team. One of them basically gets screwed. The other one has to balance. So overall neutral. So the P is going to be a +3. And you're going, but it doesn't want to be a +3. When we did this, and I did really good with this, Dr. Sherp, but it was a -3. What the heck are you doing? You're changing everything. These are not charges. Oxidation potential. That thing is going to react. That's what we're all about here. It's transformation. This is not stable because that number doesn't make sense. And so that's why we have reactions going on. All right. So those are our steps. We're going to do a little bit of practice and we'll put it all together. And I'm going to lift this up because my head keeps getting cut off. All right, let's do oxidation numbers. You can do the first one with me, or second one, or pause me and try them, and then see what happens. All right, iron and oxygen. Actually, if it's metal, non-metal, you just do what we did before. We give the greedy one, actually, its oxidation state first. Most people, unfortunately, go left to right, but it's actually, you always start with the greedy one. That means the iron is a +5. Oxidation numbers are per each atom of the element. So the iron's a +5, oxygen gets to be a -2. Now, oxygen's pretty much going to always get to be a -2. That's what it wants to be. When it's by itself, we'll get the halo. Oh, we'll see that over here twice. And then there is another exception, and I do that in one of the videos. And that's hydrogen peroxide, which is really useful because of that. All right, we give the oxygen first. This is the monkey in the middle. I don't know where, oh, my monkey's out there. I forgot my monkey. So the MN's in the middle. You do the middle one last. So compounds are written from least to most electronegative. The greediest one, you give him. Potassium's a 1A. It is a +1. 1A's are always +1. 2A's are always +2. Very few always out there. Oh, of course it's not always, because if they're by themselves, they're 0. So the Mn has to balance. So what you're going to see me doing here is I'm going to always be showing my work, is up on top, I'm going to be giving the oxidation number. And down on the bottom, I will be doing the math. So in 2021, sometime end of January or February, I forget now, we do become the year of the red ox, or the year of the bull. We're in the year of the rat right now, 2020, appropriately. The rat cheated in the race. If you don't know if you're in my class next term, you're going to get to celebrate. Because Sherpa New Year is when the big transition happens. All right, there's 4 oxygens times -2. That's what I mean by the math. Up above is my oxidation numbers. If I ask you what's the oxidation number of oxygen there, it's -2. All right, I just have 1 potassium. When I do the math, it has to equal 0. So some people teach this algebraically. It really is algebra, but just do it. Look at it. How would we make this equal 0? It has to be a 7. Positive. Now, something I didn't mention, but you might notice. So the manganese is a +7. Holy moly. Holy molybdenum. That's a huge number. This thing is awesome for doing chemical reactions. It's one of the best oxidizing agents out there. It gets a special placard because that is a huge number. When we did all the naming stuff, we worked with 2s, some 3s, 1s, 4s. Yeah, that 5, that's a big number. That guy reacts. So always show the plus or minus. Oxidation numbers always have a positive or a negative. Can't just say it's 7. All right. Oxygens. We can just give them all. Right there. -2, -2. Hydrogen. It's going to take one for the team. So really, hydrogen gets a 1. Oxygen gets a -2. And then you have to figure out the carbon. So pause me. Figure out your own carbon. All right. You starting me up again? -2 times 6 is -12. +1 times 12 is +12. So we're left with 0. Yeah, that carbon gets the little halo. Ah. You can end up with a halo within a compound. It happens. It's not common, but it does. It is just because it's an oxidation potential. That's glucose. It's probably part of why glucose ends up being blood sugar, because it does have a stability in there, but it oxidizes the crap out of you because of those oxygens. They're just never happy. All right, over here, we get +1 times 2 is +2. -2 times 4 is -8. We have to make it equal 0. We have to figure out what goes in the blank. So this would be a +6. +6 +2, that's +8. -8 will give us 0. But we're not done. There's 2 carbons. So I have to divide by the 2 carbons. +6 divided by 2 is +3. Oxidation numbers are per each atom of the compound. So before you're like, I don't understand, go back 2 minutes and walk through it, or 5 minutes. Walk through the steps, walk through these practice. It takes practice. So again, when you show up for office hours, have a constructive question. Say, can we walk through this? I understand this step. I understand that step. I got the halos. Ah, and sing for me. And then say, and then I kind of lose it. And then you can sing for me again. All right, let's do, this is a tough one. Let's do it. Barium. Barium's a +2 because it's a 2A. They're always +2 unless they're by themselves. Oxygen, right? Then there's 0. Oxygen's -2. How many oxygens are there? You guys are great at this now. There are 6 times -2. So that's a -12. There's a barium that's a +2. You don't have to show the equals 0. I'm doing that as a teaching tool. So chlorine is a +10. No, because how many chlorines are there? There are 2 chlorines. So +10 divided by 2 is a +5. That is actually why they're named 8s. That's chlorate. That's what all the 8s had in common, not the number of oxygens, but they have an oxidation state of either +5 or +6. If I taught you that, there wouldn't be many of you watching this now, because you would have been gone. And like, what? So we build up to oxidation numbers. Anyway, per means higher than a +5 or +6. +5 is a crazy number. 8s are reactive. All right. Oxygen is -2. Now, this is a polyatomic. It's one we didn't talk about yet, but it's actually really common. Now, there is, of course, there's an exception to everything. On this one, we're not going to 0. We're going actually to the charge. So when we sum them up, so each oxygen is -2. That gives me -8. The chromium is only a +6, because when we add up all the oxidation numbers, we have to be left with the charge of just the polyatomic. Now, the good news is, when we do chemical equations, the polyatomics are within a compound, so everything has to end up being that 0. But if you saw one like that, now, this is called hexavalent chromium. It's extremely reactive. Chromium likes to be a 3. That thing is like, I'm missing too many electrons. I lost too much. And it's going to steal. Really, that's what's going on. Taking them away. All right, rewind, watch it again. If you're like, can we do that one again? There's probably one in the study set. All right, ready? Here we go. We're going to bring red in for this. We're going to go back to that first page. The koi fish that you've now got. So get the first page, the koi fish. Get this idea. Now we're going to put them together. That third page, if there is another page, yeah, that is a separate video. We're going to take it one more step. All right, here we go. Still cultivating balance. Everything's balanced. Put your halos. Go, okay, I got the halos. I love the halos. Oh, and sing for me. And that will make me smile. It'll make everybody smile. All right, in the compound, oh, we already did this one. The greedy one gets the normal charge that would have, and the phosphorus basically is stuck with the +3. So what are we going to do with this now? We're going to do something called Leo-Gur. And I have to make myself more space. So we're going to erase a few of our notes. I'm videotaping. Okay. All right. Isn't that wonderful when you videotape? So we're going to write out the acronym. We can write it in red. And then we'll write our answers in black and blue. So our acronym is Leo-Gur. This is how you're going to see me do it. I write one above the other. Do it my way. It works. My students, before YouTube showed up with all these other gimmicks, my students did phenomenal. And those of you who don't trust me, do whatever you want. Leo means Leo, losing electrons. So you're always reading the direction of the arrow like we do in English. You're reading from left to right. What happened as the phosphorus went through the reaction? It had all of its electrons, had the halo. Then it's at +3, which means it lost. The chlorine goes to -1, it gained. It's just like what we were doing. We just put now a fancier word with it. That is everything. It's what causes disease, is oxidation. It's what viruses do to us. And then our body goes in, because our body knows how to heal itself, and fixes it. All right, let's do our next one. Here we go. Leo-Gur. Put your halos. Halos. Oh, now the halos can be in the reactants or the products. This one, they're in the products. And Okay, we got that 2 non-metal rule again, but you got this. Oxygen is the greedy. Unless it's with fluorine. That doesn't happen unless man made it, and then it becomes a Superfund site. And then this little girl I used to bowl on what is now a big Superfund site. Great. All right, oxygen is -2. We see the 2, 3. That means the boron must be a +3. Now, boron is not very happy with this arrangement because boron is above the staircase, so it falls apart. They go back to like the drawing board. That's what's going on here. But let's do our Leo Gur from left to right. The boron was missing some electrons, and now it has them back. So the boron actually gained. Gur means gaining. This is gaining electrons. There is another way that can help some students visually. I see some of you do great with the Gur that you can gain and lose. Gur always, as you're reading the reaction, the oxidation number drops. Leo, oxidation number always goes up. So oxygen lost electrons. So here it had extra, and now it had to get rid of them again. So oxygen is losing electrons. All right, again, I highly recommend you write the Leo Gur. The students who do that, they get it. So you just go, okay, Leo Gur. Well, how do you know? Is everything a Leo Gur? Actually not. So how do you know it's a Leo Gur? If you see a halo. And we see that here. Halo, we're going to do this. Now, we're going to go through all the oxidation numbers just because, yeah. But let's look at the oxygen. Let's just figure out what happened to the oxygen. It's at 0. And over here, it's in compound, so it is -2. So my oxygen this time is going from 0, -2 means it gained. Oh, oxygen is so happy. I often put a little X in my oxygen so you don't think I wrote a 0. All right, so something gained. Hydrogen. In compounds, hydrogen's +1. Hydrogen's in a compound on both sides. Hydrogen's +1 and it's still +1. Nothing happened. The answer is not hydrogen. It is, all we're left with is the carbon. Let's go ahead and do the carbon's oxidation number. These are tough, but we got it. We got it because we got Leo and we got red with us. All right. So the carbon has to take over here the negative. So we have +10 when we add up all of our hydrogens. So we're going to have -10 divided by the 5 carbons. That means our carbon is a -2. Okay, what happens to it over here? Oh, it's with oxygen now. Carbon and oxygen combined, the stablest thing they can make is CO2. That's what's going on. The whole greenhouse, global warming, blah, blah, blah. So, and then, so what happens is the bond and double bonds are just perfect that they reflect the heat back to us. Keeps us warm, but causes other things. Transformation. All right. If that's a -2, and there's 2 of them, then my carbon here is a +4. Those are, again, oxidation numbers. 4 makes sense for carbon. So it's going from a -2 to a +4. It's losing electrons. Or you can just think, Leo, its number is increasing like a thermometer. We were at -2 and now it's going up higher to a +4. And Gur, it drops. 0 to -2, it drops. So if the arrows work for you, great. Do that. Let's get rid of this. All right. So we write our acronym. How do we know we're doing the Leo Gur? Well, that's what we're learning about right now. Put your halos. Magnesium by itself. Over here, iron's by itself. Ah, and sing. It'll make you giggle. Giggling and jiggling and wiggling. It's great. Keep it up. All right, bromine. Look at your handy dandy periodic table. -1. And then, right, magnesium is now a +2 in the compound. Iron, to balance there, is a +3. All right, that's where the subscripts came from. We're just taking it to the next step. So rather than saying, which one's my Leo, what works better is to just say, okay, I got my magnesium here, and it changed. How did it change? 0 + 2 means it lost. So my magnesium means it is the oxidized. Because I'm not going to ask you, hey, which one's Leo? Leo would love me to ask that. But I'm going to say which one was oxidized, and you say the magnesium. Now, we do say in the product, the magnesium in the +2 is its oxidized state. But I'm just asking which element. And then the iron is my GR. GR stands for which one was reduced. The BR is known as a spectator. Nothing happened to it. It was just there, hanging out, keeping everything in balance. All right, one more, and then we have another step. All right, here we go. We write Leo GR, and then we go, oh, wait a minute, there's no halo. I don't have to do that. Get out your eraser. This one's not a red ox. It's a blue ox. I used to have a blue ox. You guys ever been down to the redwoods? There's this giant Paul Bunyan with his blue ox. So I went down there and I got a blue ox bobblehead, and it's gone. So anyway, this is not a red ox. Oh, we should write it in blue for the blue ox. Not a red ox. All right, so my little trick, no halo, it's not a red ox, it's a blue ox. That may not always work, but it will in our class. Let's go through oxidation numbers and see what happened. So aluminum is a +3, chloride's a -1. Stop me and do all your oxidation numbers. Sodium's a +1, PO4, it's still PO4. The whole thing, that's not an oxidation number. It just stayed there. Nothing happened. So the P and the O are still the same. If you want to give oxidation numbers, should we do it? Let's do it. Oxygen's a -2 times 4 is -8. Sodium's a +1. So the P must be a +5. And over here it's still a -2 and a +5. And the aluminum's a +3. There's a lot of oxygens there. That's what's balancing that whole +8 is all 4 of those oxygens. And the sodiums are still a +1 and a -1. So a really good question, and somebody always asks, those koi fish, remember the koi fish? They have no effect on oxidation reduction. So don't worry about them. All right. So we actually have 2 more steps we're going to do. So the one is on the previous page. There was a question at the bottom of the page. I knew it was there, but I go through all of this. If you need to, you always do the Leo GR first. Actually, you balance your equation, the koi fish, you do your Leo GR. Now we're going to do something called the OA and the RA. This is how I teach it, and what I found is the students who do it my way, because that's what you're going to see, that's the visual you're going to have. They get it, they've got it, they're good. So, what the OA stands for. Okay. Sorry, I'm looking for my eraser. It's probably in my hand. I'll just have to use a hat. So, OA means oxidizing agent. Anybody want to guess what RA stands for? Reducing agent. So, oxidizing agent causes oxidation. So whatever is reduced is the oxidizing agent. These guys are going to crisscross. I always do my O's first. I always crisscross. That's just how I do it. So whatever is reduced, it's gaining electrons because it causes the other one to be oxidized. So it is called the agent of oxidation, or the oxidizing agent, or the oxidizer. So let's do it in chlorine. And the phosphorus would be the reducing agent. Now, these are causes. These have to be the whole reactant. When we did the Leo-Gur, this was just an element that changed. So let's just go through it. And again, this is why you have study sets and lots of practice. We do lots of practice with this. All right, so we crisscross. The O's always go on top. So my boron is going to be my oxidizing agent. But it's not boron. It's how the boron started, which is B2O3. And here, the oxygen is going to be my reducing agent, but it's how it started in the reaction. Yeah, so we have kind of a double agent. That happens sometimes. Get the same answer twice. It's not very common, but we'll see why when we look at reaction types. All right, let's do OA, RA, crisscross. Oxygen, we write it as O2, and it's C5H10. So a comment, if you notice how I do it, I write the Leo-Gur, and then before Leo-Gur, I write my oxidized, my reduced. And then I do my crisscrosses in the middle, and I write my OA, RA, and those are on the outside. If you try to write stuff in the middle, you're going to not know was the carbon oxidized or the oxidizing agent. All right, we want to do it one more time, because the last one, if it's not a redox, there's no Leo, there's no Gur, there's no OA, there's no RA. All right, so the iron is gaining, but how does the iron start? It starts as FeBr3. So it's how the iron starts. How does the magnesium start? Well, it does start as magnesium. And that's it. I did promise there's one more piece we're going to add, because this is such a nice page. There was lots of room for you to write on. I would go back and do it again, and then you'll be ready to add the next step, which is the next video, which is writing them from scratch, and you're going to be great at it. That's why we have a whole lab. So there's actually 2 videos where I walk through writing them from scratch with different types of reactions, and then you'll be good to go and do it on your own. And we get practice with this. We're going to add one more piece to this, just so in a couple weeks when you go back to do this again, when you're studying, you have the example there. By then, in the lab, in the next videos, I go through types of reactions. We'll worry about it there, but these are the 5 reaction types that we're going to learn in those videos. So I'm going to write the names so you can have them in your notes. Don't worry too much about it. But this first one is called a combo, or a combination. So we're combining things together. We have one product. This one's called a decomp. We actually saw this word, I think, at the very beginning of the term. Decomp means decomposition. The whole word's written out there for you in the next set of notes. So it's decomposing. It's a compound that had issues, and it just breaks apart. It doesn't have a breakdown, it just breaks apart. I mean, these are serious issues. Just did not work. And it's usually an oxidation number. Pretty much is an oxidation number. All right, the next one is called combust. Combust means to burn. Burn, baby, burn. This is pentene burning. So burning means with the oxygen. So it's a carbon hydrogen compound with the oxygen. All right, the next 2 are exchange reactions. I call this one a single, and this one a double. So a single is because you have a single element, and now you have a different single element. So they exchange. There's an exchange going on. In the double, if you look, they exchange their partners. They each had a partner. It's kind of like tennis. You have double-double. You have new double-double. Double-trouble. The thing is, everyone loves the doubles. Everyone gets them. And I think it's because doubles are never, ever. Very few never-evers out there. Let's see the whole board so we can remember that we're cultivating balance in all our endeavors so that we can experience greater energy and vitality. But these are never ever red ox. The double troubles, they're always the blue oxes. All right, and so with that, the koi fish, people must think I'm a little cute and cuddly little girl because people buy me a lot of stuffed animals. But Leo and Red and the koi fish, we all wish you a beautiful day. You can do this. Bye-bye.